Okay, so we are going to be on starting on 5.2, and we're going to learn how to do these different electron configurations that you started to look at yesterday. So atoms are stable because of the way that their electrons are arranged. This arrangement allows for the atoms to be stable. If the electrons were in different arrangements, they would not be stable and they would be highly reactive, and it would be very difficult for compounds to form, or it would be difficult for compounds to maintain their form, for proteins to maintain their form, for anything that involves atoms, which is all matter, to maintain their form. If every atom was very unstable because of its electrons, then we would have a really difficult time maintaining the shape of matter and maintaining certain types of matter. There would be no stability. So this energy of electrons and the stability of electrons determine this thing called electron configuration. And the configuration, you can think of configuration as arrangement, as the arrangement of electrons within an atom. So we're just going to be learning. We've looked at the quantum mechanical model and how that we have broken that down into two kind of components used to describe an electron's location. We looked at the principal energy levels, right? And those are our n numbers, and so this tells us how much energy the electrons have. Then we looked at the atomic orbitals, and those were the shapes, right? Like here. So we had the s orbitals, the 3p orbitals, and the 5d orbitals. Okay, so then we got to this, and this was a nice, remember, summary table of, I'll erase this over here, of everything that we had talked about so far. And we said, I'm going to just, whoa, erase all that. We said that in the first, we're only going to talk about the first four principal energy levels, remember. So the number of sublevels in N1 is 1s. But what does that really tell you? That tells you that there's two electrons. Remember, each orbital can hold two electrons. So there's two electrons in a spherical pattern. Okay, well, that's not super hard to figure out, but there's actually more detail we can go in. They're not just going in this, like, are they going in the exact same direction? Are they right next to each other? What do they look like? And how do we denote this? Do I have to, if I wanted to describe an element that has two electrons, like helium, if I wanted to tell you that it has two electrons, there's actually, like you saw yesterday, there's a certain way of diagramming this and writing these things. We don't just say or write out, helium has two electrons in the 1s orbital, right? We don't write it like that. That's not what we're going to write every time. If we wanted to draw the helium, the diagram, the electron configuration diagram for helium, square, it would look like that, right? So that's just helium. That's the simplest one, or not hydrogen is more simple, but what about when we get to something that has like this, like up here in the N4 level that has 32 electrons? Or how do I draw something that has 3 electrons, right? I'm only telling you in the N2 sublevel when it's completely filled, or in the N2 principal energy level when it's completely filled, it can fit 8 electrons. But what if an atom only has 6 electrons? Or what if it has 5 electrons or 3 electrons? How do I write this? How do I denote this? So we're going to use this thing called electron configuration. We're going to use the principal energy levels, the atomic orbital information that we just went over, and we're going to write these electron configurations. So the definition of what is an electron configuration, first of all, you can think of it as the way in which electrons are arranged in various orbitals around the nuclei of an atom. Okay, so there's the definition of that. I was just told by my dear husband that I speak too fast when I'm explaining these things to you. So, sorry, my bad. He also is not a native English, not as good at English as 99% of you are, so maybe that's his problem, not mine. But anyway, I'll try to speak slower. So, electron. Okay, I'm not going to speak that slow. There are three different types of electron configurations. And here's the definition that I just gave you. I just wrote it up there, so if you want to pause it and write it down, but you probably already have it written down from your note-taking or from the assignment from yesterday. Okay, so there's three different types, or there's not three different types, but there's like three different ways that we can write electron configurations. We can do electron configuration diagrams. And these are, I'm just going to show you what they look like. So, for example, actually I'll get up the same picture up here from your notes. All right, so this is what the diagram looks like. The electron configuration diagram, actually drawing it and diagramming it. And this is actually technically not exactly how we would do it, because when we draw it, like for example, if I wanted to draw nitrogen here, I wouldn't separate the three P's like this. I actually draw them. It would look like this. Oh, that's too small for my big fat pen. Okay, it would look like 1s, 2s, 2, and then I have 1, 2, 3 in the p orbital. So I actually draw it all connected like that. So everything's the same, it's just there's no spaces in between there. And then this would be 2p3. And you can write, if you need to remember, see how they, well, I'll explain that in a second when I get more into it. So that's the only difference between this diagram that I showed you. We actually just draw the p orbitals connected, not disconnected like this. Okay? All right, so that's the configuration, electron configuration diagrams that we can have. Another way that we're going to write or learn how to write these electron configurations is with longhand. That's the next, so this is number 1. Number 2 is with this longhand configurations. I'm just going to write config. And that would be something like 1s1 or 2s2 or, well, it would be like 1s1. For hydrogen, it would be 1s1. For helium, it would be 1s2. For lithium, it would be 1s2, 2s1. So this is like, we're not drawing any arrows or any boxes or anything. We're just writing out all of the letters and the locations. And I'm just explaining and giving some brief examples of these, and then I'm going to go back in detail and we're going to go over them together. So the third way that we're going, that's the last way after we've mastered drawing the electron configuration diagrams and writing the electron configurations in longhand. Then we'll do shorthand electron configurations, but these are also called noble gas configurations. So a way that we could do that would be He2S1. That would be this would be lithiums. For, who's next on the periodic table? Lithium, and then I think it's magnesium. I might be wrong, but no, it is. It's not magnesium. It's barium, I think. That would be He2S2. So we have these noble gases, which I will explain what a noble gas is once we get here. Okay. So we are going to have to talk about electron configurations. We're going to start with the diagrams because I think that's the easiest way to start. Diagrams and then longhand, and then we'll do shorthand last. So we have 3 rules that we need to follow when we're writing electron configurations, and they are actually the rules that tell us how we write them. So we have 3 rules for writing and also, just so you know, these 3 different types or 3 different like the diagrams, the longhand, and the shorthand, they're not three different things. It's three versions of the same thing. It's like how I could write my name in all caps, or I could write my name in cursive, or I could write my name in all lowercase. It's like that. It all says my name, but it's just three different ways of writing or drawing or depicting the same thing. So I just want you to know we're not learning three different things. It's just three different, or three varieties of ways to draw or explain electron configurations. So let's look at our three rules. Then we can get into the diagrams and the longhand. The first rule is called the off-bow principle. And this rule states that electrons occupy the orbitals of the lowest principal energy levels first. So remember that we have 7 principal energy levels. Remember the n number. We have n equals 1, n equals 2, all the way up to 7, right? And we know, because of quantum mechanics, we're only going to do up to 4 here. We know that this one is the lowest energy. The first principal energy level is the lowest, and it goes, the fourth would be the highest. So it increases in energy. So if we're at the n equals 4 energy level, principal energy level, we have much more energy at that level than we do at our n equals 1. So another way of saying this is that the n equals 1 is the most stable of the principal energy levels. Okay, within each of these principal energy levels, we have different orbitals. Remember, we have s, p, and d orbitals, and f, but we're not going to get into f. Based on this table that we looked at, remember that in our first principal energy level, in n equals 1 here, we have one sublevel, and that is an s orbital. So in the first energy level, we have one s orbital, or sublevel, we'll say. Right? So the way that I write that, if I wanted to describe an electron that was in the 1s, I would write exactly that, 1s. This tells us our n number. This tells us our sublevel. Okay? So I'm explaining that to you because when I bring this picture up, it might look confusing at first, but it's really not confusing. So remember, in the second energy level, we have go back. We actually have 2. All right, we have one s orbital and one p orbital. Or sublevel, whatever you want to call it. Same thing. Remember, they're interchangeable, but I'm going to stick with sublevel. All right. So if I wanted to write this, how do I differentiate between, there's an S sublevel here, right? The 1S sublevel, the S sublevel in the first principal energy level. But how do I differentiate between this S sublevel in the second energy level and the first one? I write 2 because I'm in n equals 2, so my n number is 2, but I'm talking about my s orbital. And the same thing for p. So I would have a 2s and a 2p sublevel. So the reason that all of that is important is because in order to understand Aufbau, however you say it, his principle, we need to understand what each of these letters and things mean here. So we have this diagram that's from your book and from your notes. So we have our 1s, our 2s, and our 2p, 3s, 3p, 3d, 4s, etc., etc., etc. So the place that they are shows us how much energy they have. So 1s, remember, it has the least energy. It's the most stable. It has the least energy. Therefore, it's at the bottom because we're increasing in energy as we go up. So 1s has the greatest, or the least amount of energy, the greatest stability. Up here are the highest one they go to is the 6p. The 6p orbitals, that has the greatest amount of energy and it is the least stable. Okay, so what Aufbau's principle says is that electrons are going to occupy orbitals of the lowest principal energy first. So in our diagrams that you've seen, I always start with 1s, right? And then I put these arrows, which hopefully you know from your reading and watching the videos yesterday, that means electrons. So electrons, each one of these squares, all of the squares, every single square can hold 2 electrons, okay? So we first fill the electrons in the 1s orbital, then in the 2s orbital. So if I have 4 electrons, the first 2, let's erase this. If I have 4 electrons, okay, 4 electrons, I want to know where am I going to put them? How am I going to arrange them in my electron configuration? Aufbau's principle says that first we're going to fill up our lowest energy level. So the first, we're going to have to place 4 arrows in 4 different, in these orbitals. So the first 2 are going to go here. They're going to go in our lowest energy level. The second 2 are going to go in our next energy level, which is the 2s. There we go. So if I had 1 electron, well, you understand, I think, I hope. So this is what it would look like, the electron configuration diagram would look like for 4 electrons. We start at the lowest energy level and we go up. So if I had these 4 electrons still, I would not start putting them in at the 6s. That doesn't make sense because 6s is way the heck up here. We have to start at our lowest energy level first, okay? So that's all that his principle is saying. You start at the lowest energy level and fill your orbitals from the lowest to the greatest, okay? I think that's all for his principle. I think that's pretty much the easiest way to explain it. I gave you, yeah. Okay, let's look at the second one. All right, so the Pauli exclusion principle is the second rule for how we're going to write electron configurations. And this principle tells us that an atomic orbital may describe at most 2 electrons. And in order to occupy the same orbital, the electrons must have opposite spins. So let me write that definition down and then we'll break it down a little bit. All right, so the first part here is that the atomic orbital may have at most 2 electrons. So when I'm saying the atomic orbital, remember I have different shapes and different types of orbitals. I can have the s, the p, and the d orbitals. And in an s sublevel, we have 1 orbital that can hold 2 electrons. In the p sublevel, remember how they've been drawing them as 3 separate pieces like this? Well, really, it's just we draw them together like this. But this is 1 square, 2 square, 3 square, right? So there's 3 orbitals inside the p sublevel. So each one of those orbitals, you can think of as an orbital. Orbital just is a square, right? So this has 3 orbitals. This has 1 orbital. And the d sublevel, remember, has 5. This has 5 orbitals, okay? And each orbital here each one can hold 2 electrons, okay? So in our s sublevel, we have 1 orbital that can hold 2 electrons. The Pauli exclusion principle says that every single orbital, so every single square, it can only have 2 electrons. So I cannot have 1, 2, 3 electrons in here. That's impossible. I can only have 2 electrons in an orbital. And they must have opposite spin. So what that part means, let me scoot over here. What that means is I have my nucleus, and let's just look at the 1s orbital that has 2 electrons. And remember how I showed you that the electron diagrams, we keep having these arrows up and down, right? What that indicates is the spin of the electron. The electron can either be spinning, since this is an s orbital, remember that means it's spherical. So the electron can be spinning in a clockwise direction. Spin can be clockwise. Or an electron can be spinning, let's have another electron over here. Let's say this electron is this one. It can be spinning in the counterclockwise direction. Okay? So every single orbital can hold 2 electrons, but they must have opposite spin. We must have 1 electron with a clockwise spin and 1 electron with a counterclockwise spin. And the way that we draw that is by the direction of our arrows. So actually I'll go back here. Let me give you the definition of spin here. All right, so it's the quantum mechanical property of electrons thought to be clockwise or counterclockwise in direction. When we're depicting or drawing this, a clockwise direction is an up arrow. A counterclockwise direction is a down arrow. So Pauli's exclusion principle states that every orbital, every square, can only hold 2 electrons, and they must have opposite spins. So if I drew it like this, that means I have 2 electrons with clockwise spin. That is impossible. I cannot have that. Likewise, I cannot have, let me redraw it, 2 electrons pointing down. That means I have 2 electrons with counterclockwise spin. I can't have that either. I must first put my clockwise, my up arrow, then I can put my opposite or my counterclockwise electron. Every single orbital must have, it can only hold 2 electrons. It could have 1. I could just draw 1. That's fine. But I cannot have 2 in the same direction. And I cannot have 3 electrons, even if they're in opposite directions or whatever. I can't have 3 electrons within an orbital. An orbital can hold 2 electrons, and they must have opposite spins. Those opposite spins are up, meaning clockwise, and down, meaning counterclockwise. Right? Okay, so that's Pauli's exclusion principle. Now our final rule is Hund's rule. Hund's rule states that electrons occupy orbitals of the same energy in a way that makes the number of electrons with the same spin direction as large as possible. Another easier way of saying this is that orbitals are occupied with electrons with an upward arrow or a clockwise spin first, and then with a downward arrow or a counterclockwise spin second. So let me write that. All right, there's everything I just said. So the easiest way to look at this or to understand this is to look at some examples. So I have an atom with 7 electrons. 7 electrons. All right. I want to know how I'm going to draw my electron configuration diagram. So, because of Aufbau's principle, we know that we must put our first electron in the 1s orbital because that's the lowest energy level, right? Hund's rule, didn't mean to do that. Hund's rule says that the electrons must go into the orbitals upward arrow first. So the clockwise electrons go in first. So the first one I'm going to write is an upward or clockwise spin electron. Okay, so that's one electron. Now I have 6 more that I need to place. So I have to, because of Aufbau's principle, I have to fill up the first energy level before I can move on to the next one. This is also Pauli exclusion principle. It says that we can put 2 electrons in each orbital. So this is one orbital, so it can fit 2 electrons. Pauli's exclusion principle says that we need to have opposite spins. So here we go. So that orbital is filled, but I still have 5 electrons. So where am I going to put those? Well, remember this diagram. Oh, no, I went back too far. Here. Remember this diagram. I'm going to bring you over here. Hold on. This will help us if we have this here, I think. Okay, this diagram shows us that the next energy level is the 2s. The 2s energy level. Well, all the s orbitals have only, the s sublevels only have one orbital or one square. So that's how I would draw an empty 2s sublevel. Okay? All right, so now I need to put my electrons in here. So I have 1, 2 electrons. Now I'm on my 3rd electron. So because of Pauli exclusion principle and because of Hund's rule, mostly to start actually, we know that we have to put our our clockwise spin first. Because of Pauli's principle that says we can have 2 electrons in each orbital, I know that I must put my second one in, but it must be in the opposite direction. So now I have 4 electrons placed. Okay, so I've put 2 in here, 2 in here. Those are completely filled. Because of Pauli exclusion principle, I can't put a 3rd one in here, right? So I need to go to the next orbital in the energy level, which is the 2p. So I'm going to move this guy down here. All right, so we've filled this one, we've filled this one. Now we're going to go to our 2p. So to draw that, remember, I'm not going to split it up into three different separate boxes. I'm actually just going to make them a big rectangle and then split them like that. So this is my 2p, okay? All right. In my 2p, I'm going to have to place 3 more electrons, right? Because I have 1, 2, 3, 4, so I have 3 left. So because of this rule, Hund's rule, and because of, Hund's rule mostly, I'm going to put this one first. Okay, so this is where Hund's rule really comes into play. You would think maybe that you would put, that would be your 6th one, and this would be your 7th. But that is not correct. Hund's rule, this is correct, but the other 2 are not. Hund's rule says that electrons occupy the orbitals of the same energy level, so that we understand that makes, in a way that makes the number of electrons with the same spin direction as large as possible. What that means is first we put in all of our positive or our upward facing arrows. All of our clockwise electrons must be put into the sublevels first. If that's the case, I know that I can't do this, right? Because that breaks Pauli's exclusion principle. So the next place that I must put an electron is here. So I have 6 electrons now. The next place I'll put an electron, my 7th electron, will be here. Because I want to maximize the number of clockwise spinning electrons. You can think about this as like, this is the most stable way for electrons to exist. So we have, let's really think about, this is going to be the last thing I'm going to talk about, and then tomorrow we're going to start writing our electron configurations, but this video is almost over, so bear with me. So let's think about what this 2p sublevel looks like, okay? like really what it looks like. So remember that 2p, we have, let me get my picture. In my p sublevel, these three, I have three different directions that, or spaces that these electrons can occupy. So you see here I have a px, a py, and a pz. That x, y, and z tells us which axis the orbit can be on. So here we have electrons spinning on the x-axis. This is the x-axis, this is the y-axis, and then the z is kind of going like out, or up in this case. Okay, so we have px. So you can think about this as px. So I have one electron in the px spinning in the clockwise direction. So clockwise would be like this. Okay, so it's spinning in the clockwise direction. Do you think that it would be safer or more stable or more stable, we'll say, to put an electron right next to this electron? So this has one electron here, as I've drawn one electron, right? Would it be safer to put an electron in the opposite direction right now? Or would it be more stable to put it, since I have these two other places, these two other whole empty areas for electrons to be, would it be safer or more stable to put this electron right next to the z, like right here, in the opposite direction? Or would it be more stable to just put the next electron spinning in a clockwise direction in the y orbital, for example, like here, like how I have it drawn here? We're separating them more. There's more distance between the electrons if I put it in the y rather than putting that second electron right next to the first electron in the px orbital. So that's why I put the next one in the py orbital. So we could draw, this is py here. Same thing with the third electron, the final electron in these 7 electrons that I'm looking at. Is it more stable to put an electron, again, in the counterclockwise direction in px or in the counterclockwise direction in py? Or would it be more stable and less energy to move the electron over to the pz orbital? It makes more sense that it would go to the pz orbital, right? Because we want to spread them out. Remember, electrons don't like each other. This likes repel likes. Negatives don't want to be around negatives necessarily, right? So we want to spread them out as much as possible. So that's basically what Hund's rule is telling us. So I'm going to do one more example with 9 electrons. Okay? So I know that I have to start with my 1s orbital. I'm going to do 1 up, 1 down. Then I'm going to move to my 2s orbital because of Aufbau's principle. 1 up, 1 down. They have to have opposite spins. Then Hund's rule comes into play here. We have our 2p orbital. All right, so here I have 4 electrons already. So Hund's rule tells me that I must put all of the upward facing arrows in first, then I have to go back and fill in the downward facing arrows. So I have 9 electrons here. So I've already put in 4, so I have 5, 6, 7, 8, 9. That's how I would draw. That's how you would draw an electron configuration diagram for an atom with 9 electrons. And if we look at our periodic table, here, number 9 on the periodic table, where's number 9 on the periodic table? It's fluorine. So this is actually what we've drawn here is fluorines. I can erase an atom. The atom with 9 electrons is fluorine, right? So this is how I would draw the electron configuration diagram for fluorine. The only thing I'm missing here are these little numbers, and this just tells me how many electrons I have total in that sublevel. So for the 1s, I have 1, 2. So I put a little 2 up there. So 1s2, that means that this sublevel, this 1s sublevel is filled. It's filled, we say. For my 2s sublevel, I have 2 electrons. So I write 2s because I'm in principal energy level 2, this one. I'm in the s sublevel, and I have 2 electrons. So it is also filled, meaning I can't fit any more in there. Then I have my 2p, and how many electrons are in here? 1, 2, 3, 4, 5. So I have 5 electrons in my 2p sublevel. So this one would be partially filled. And we're going to start there tomorrow with what I mean by filled, half filled, and partially filled. Okay, so you have a couple questions to answer. And then we will finish with this video. Actually, no, you don't have any homework for today. You just need to watch this video because it's pretty long. Take notes. And then tomorrow you will have a homework assignment that will be due on Friday because Thursday we do not have class. So please let me know if you have any questions. You might have to watch this more than once because I know that this is one of the most complex things we'll do in chemistry, and I love it. It's so nice. We're going to be able to write the electron configurations like we've done here for fluorine. We're going to be able to write these for every single atom up here. So that's where we're going. Please let me know if you have any questions. No homework. Just make sure you've watched this entire video. Thank you.